lost it.
Recording is on.
Oh my god. Recording is on. All right, cool. So we'll give it another like minute, I guess, and then we'll jump into it. I don't want to wait too long.
Yeah.
All right, 30 seconds and counting. All right, I want to go. Let's go. So yeah, so I'll just go ahead and share this YouTube video first, and then we can talk about it. So let me know if you can see this. Can you see this all right?
Looks good.
Awesome. Yeah. Okay, so I'm gonna hit play and
projects to go. We have some closing remarks, so things that will be. So we're jumping in.
People who just started or who just joined, let me just check really quick. People who just joined, I'm playing a YouTube video, so let me know if you can't see the YouTube video.
I can see it.
All right, perfect. Hello, my name is Jordan Ellis, and I also worked with Roberto Henriquez Perozo, Cesar Brazon, and Ori Shimoni, all living in the US and Spain and members of the dOrg family. We're here today to bring you Web3 API. Web3 API is a developer toolchain that brings the ease of Web 2 to Web 3. It enables multi-platform and dynamic Web 3 applications. Integrating Web 3 into your applications today is difficult and slow. App developers and protocol developers need to be in constant coordination to maintain compatibility and support new functionality. JavaScript smart contract SDKs limit dApps to just the browser. Pre-build steps hinder developers' ability to build dynamic applications. And lastly, JavaScript limits performance and creates attack vectors. We can do better. We built a Web3 WASM runtime for universally compatible smart contract APIs. This allows protocols to implement user-friendly wrappers in a language-agnostic way. These WASM modules, paired with a subgraph for historical data querying, combine together to create a single GraphQL schema that defines the entirety of the protocol. We call this GraphQL schema a Web3 API. Web3 APIs live on IPFS and are addressable using ENS. They can be queried from any language or platform: Node, browser, C#, C, C++, Rust, Go, Python, etc. dApps only need to include our lightweight client to query any Web3 API. Here we can see an overview of the architecture. At the bottom, we have our multi-platform applications that all include their various versions of the Web3 API client. This client library enables the querying of any Web3 API given its decentralized API endpoint, also known as an IPFS hash. Once the Web3 API is downloaded and all necessary WASM modules are loaded at runtime, queries can now be executed. These queries may lead to interactions with various peer-to-peer networks such as Ethereum, IPFS, and Graph Protocol. In summary, Web3 API instantly integrates into your applications, runs on all devices, and interacts with your favorite peer-to-peer networks. And so let's see a demo. So here we have an example project. We created a simple storage project, which is a lot of people's first project they jump into when they start developing on Ethereum. The first thing we'll do is we use the Web3 CLI to set up our test environment. This is where we have a subgraph, graph node, we have IPFS, and we have Ethereum running in the background. Next, what we'll do is we will deploy our contracts to the Ethereum network. This is using Ethers.js. You can use any other Web3 library you like Web3.js or Bidler or Truffle. And then lastly, we'll build the Web3 API. What this is doing is it's compiling the query and mutation WASM modules. It's building out the subgraph using the Graph CLI. And then lastly, it's uploading the whole project to IPFS. And so here at the bottom, we can see our handy URIs for our project. And so if we wanted to see what this project looks like, we can go ahead and paste in the IPFS hash into a browser and see the contents. This is our build folder. This is our Web3 API manifest, which describes the project as a whole. We also have our schema, which defines our mutations and our queries. We have the mutation and query WASM modules and our subgraph as it is normally built. And so now that we've talked about the build step, let's actually see what using this looks like. So normally you would probably be familiar with writing your tests in JavaScript or some other language. We wanted to create something a bit different and simpler, which is just a series of GraphQL queries in a JSON recipe. And so as we execute this JSON recipe, what it will do is it will go ahead and call the get function on the smart contract, the set function. Here's our transaction receipts. We can see that the value is changing as we make new sets. And then lastly, it's querying the subgraph. And so all of this is in this little query recipe here, which links to these query documents. If we look at what these look like, this is just a simple GraphQL query. This is all that an application developer needs to understand in order to use your protocol. And then the protocol developer who's implementing these mutations would compile them to WebAssembly. This is an example in assembly script where we're interacting with the Ethereum network through the WASM runtime of Web3 API. As you just saw, through the magic of WASM and GraphQL, we're able to bring smart contracts into applications with lightning speeds. The impact this has in the Web3 space is immense. We now have a blazing fast dev loop, multi-platform support, dynamic dApps, and secure and efficient SDKs executing inside of a WASM virtual machine. Here's where we are currently at in development. And here is what we're looking to do in the immediate future. And here's our current North Star, the Web3 Hub, a place for developers and users alike to discover, use, and fork Web3 APIs for their specific needs. Web3 Hub will allow users to visualize the GraphQL schema, query the API in its entirety, and publish user-friendly dashboards at the drop of a hat. Here we see an example of a DeFi protocol which has dashboards for its governance stakeholders, liquidity providers, and traders. If you'd like to join early access or become a governing stakeholder of the project, please join the mailing list at web3api.dev. If you're interested in joining the development team, please contact myself or anyone else at dOrg. Come help evolve Web3 with us, and hopefully we can make the world a better place. Thank you.
Thank you so much, Jordan. It was a really cool demo.
Cool. So let me stop this really quick. Yeah, and so hopefully that gave a quick once over. And if any of you have any questions, please feel free to ask them, and then I can talk about more specific parts of the project.
Yeah, so I was wondering, so your Web3 API, it includes a bundled subgraph, so you can make a call and then get like an optimistic result back before it confirms on the blockchain. Is that correct?
Okay, so that's kind of bundling together two things. So let's break those two things apart. So first off, yes, a part of the Web3 API is the subgraph. What the subgraph is used for is, being able to store historical data from the blockchain events that are emitted. And so, for instance, if you have a bunch of mint events on a token and you want to aggregate those to find like a current balance, you could do that using a subgraph. And that subgraph schema is kind of just it's just put there adjacent to the Web3 API schema. And so it basically, sorry, I got distracted. And so your Web3 API schema has these queries and mutations which execute WebAssembly, and then it also has the full schema of the subgraph, which could be, like your reputation holders, all of the DAOs, all the proposals, all the exchanges, et cetera, all of the swaps. And so, yeah, subgraph is a part of the Web3 API. It's used for the historical data.
Right, and then you can optimistically store results in the UI.
Yeah, so now how do you achieve optimistic UI? So that can be done through just standard GraphQL tooling. So since this is all exposed through a GraphQL interface, you could use, like for instance in JavaScript, the Apollo client to be able to do optimistic results. And so there's nothing actually special that we have to support in Web3 API to achieve the optimistic UI. It's kind of just like baked in there because we use GraphQL and GraphQL tooling that is kind of built around the GraphQL standard can support optimistic UI. So yeah, that's totally possible. Mm-hmm.
Cool, thank you.
Yeah. Awesome. Any other questions? And if there aren't, then I can just dive into some of like the nitty-gritty details that I found really interesting when having to implement this. Yeah, but I'd love to just answer any questions you all have about your own thoughts and understandings. And yeah.
Yeah, I think that plan sounds good. Just interested in getting further into the details, especially regarding the WASM modules.
Amazing. All right, so yeah, let's actually just jump into the code then, and I'll talk about how it's all implemented. Cool. So first off, let's look at this simple storage example project. This is a subfolder of the project. So if we go to the prototype repo, all the code for the project is in this prototype repo. It's a mono repo. And then there's this demos folder. And so here we have a simple storage demo. So that's what I will show you first, so that we can see what it looks like to a user. So since a lot of us here are probably most familiar with developing apps, let's look at what it looks like for app developers to use Web3 API. So the first step is you would basically import the Web3 API client. And so here we have Web3 API. You would create your client. So step one is create the client. So create and connect the client. And so we're connecting this client object to simplestorage.eth, and at this ENS address is going to be where that where the Web3 API package lives. It basically points to IPFS, and then you can download the full package from IPFS. And then we then give it these portals, and so what portals are is they're basically objects that, or you know, they're modules that allow you to connect to peer-to-peer networks. And so here we have an Ethereum portal, IPFS, and a subgraph. And so these allow you to connect to Ethereum, IPFS, and a subgraph. And in order to instantiate these, you simply give it a provider. And so here we're creating Ethereum with a MetaMask instance from the window object. You could imagine that instead of this, you could use like Web3 modal or something like that to choose your provider, and then you would just pass that in. And for IPFS, we give it just, you know, a simple endpoint, and the same thing for the subgraph. Next, what we want to do is we want to actually query. So, you know, step one is instantiate, and then step two is use. Like it's that straightforward. It's just create and use. So, you know, use the Web3 API. And so here what we're doing is on simplestorage.eth, if we actually look at what that package looks like, if we look at what simplestorage.eth's schema looks like, here's the schema. Let's make this a little bigger. It has a mutation object with set data and also deploy contract. And then it also has get data as a query. And so here, what we want to do is we want to set data. And so we go ahead and we create a query. We give it a mutation with set data, the address, and the value. These would be passed in as variables. So we'd have address, and then we'd have value. And when we execute this query, we get a result back. So, and then you can do result.data.setData. I believe this is the syntax for the result that's returned. And then this would give you the string that's returned from setData, which ends up being your transaction hash. And so this interface here is exactly the same as any other GraphQL client. And so you could imagine that if you wanted to use this with Apollo client alongside maybe like some other Web2 GraphQL schema, you could simply wrap this in an Apollo link, and you could just add it to your client. And yeah, doing that, like wrapping it in an Apollo client would allow you to do optimistic updates. Since Apollo client has like a local cache and it does the local data fetching and can give you optimistic results in return. And so, yeah, like in order to support that better, you know, you could imagine that we had maybe like, you know, Apollo client from, you know, at Web3 API client Apollo JS or something like that. And this is just our like, you know, wrapped version to just make it really easy for users to do optimistic UI. And so, yeah, that's the user from the application. In order to actually find these APIs, like we're planning on building the Web3 Hub. And so what that looks like is presentation. What that looks like is if we go down to this slide here that I just want to show you really quickly, this is what it looks like. It's very similar to GitHub, where you can type in, let's say, Uniswap, and it'll show you the uniswap.eth Web3 API. And here you'll be able to see the schema. This is just like a visual GraphQL schema viewer that's open source. So like we can just use this to make our UI look really nice. And they can, you know, poke through the schema, see what queries there are, see what types there are in the subgraph. They can query it inside of the application, so they could just type in these queries really quickly to just test things out inside the browser. And so maybe, you know, you want to test out set data, and you don't want to build an app to test it. You could just test it in Web3 Hub, just right away here. And then thirdly, there could be like dashboards. This is kind of an auxiliary point. But yeah, so that's kind of the user flow of using Web3 APIs as an app developer. Do you guys have any questions about that? And if not, I can jump into the protocol developer's perspective. Cool. All right. So now what does it look like to use or to actually build this simple storage Web3 API? So for that, we'll go into the protocol directory. We can check out the source. First thing, I guess, to note here is that, you know, the package manifest here describes the layout of the project. So we have our mutations, which has a schema, and it also has a logic module that compiles to WebAssembly. And then for the queries, we have the same thing. We have a schema and then a logic module, which compiles WebAssembly. And then lastly, a subgraph. And so if we go into the source directory, we have our contract as we normally would, our simple storage contract. We have the compiled version here. So you would, you know, build your contract like you normally would with Truffle or whatever else you'd like. And then you would develop your mutations and queries, and then also your subgraph. So I'm not going to cover the subgraph since I think that everyone kind of, you know, well, if you don't have familiarity with the subgraph, you can go check out their project and understand how to create one. It's basically just like loading in events. Here we're grabbing an event, data set event, and then we're modifying the database. Here's the subgraph manifest, all that stuff. And then here's the schema. So we have like a simple storage object in the schema. And so what we're doing is we're adding queries and mutations alongside the subgraph. And so here, if we check out the query, let's say, if we look at the schema, we have a get data function. And then the implementation of this query is right here. The implementation is right here, where we say function get data, and then we do ethereum.call the view function get, and it has no arguments. So we're basically just calling a function on a contract to get the current value. But the important thing to note here is that this is, you know, a full programming language here. So you could program anything else you'd like here. For instance, let's say maybe we wanted to average all user data or something like that. Or maybe we wanted to like fetch data from IPFS or fetch data from subgraph. We can do that if we include, let's say, IPFS or subgraph. And then we use those as such. We can do subgraph.query and then give it a query. Here, we can do IPFS dot add, and then we can give it data. Or we could do cat, and then we can give it an IPFS hash, and then get that data. And for averaging all user data, we could do like data.length. Let's just do address.length. Sorry. Anyway, yeah, you could program a for loop. So yeah, that's kind of the cool part. And so all of the things that you're used to having in, let's say, your JavaScript clients for protocols would be written in WebAssembly, so that way it could run anywhere, and it could be compiled and then downloaded at runtime and executed at runtime. And so it's more or less the same thing for the mutations. Here we have mutations for setting the data and deploying the contract. Then if we look at what the implementation of that looks like, we have set data, where it sends a transaction to the set function. And then here we have deploy contract, where it calls deploy contract with the ABI and the bytecode. What was I going to say? Yeah, you may be asking, like, why are queries and mutations separate? It is because you may want to have a read-only application, and this allows you to very easily only allow the app to execute queries and not allow it to execute mutation queries. And so you can imagine that as soon as you hit a button that requires you to sign something, it would basically ask you, hey, do you want to allow this app to access your private key or something like that? And it's like, okay, yes, I do. And then it'll allow it to actually execute the mutation. And like the plan is that this send transaction function won't even be available inside of this query module. So if you tried to do Ethereum.send transaction here, this would actually give you an error because it wouldn't exist for you. So it's just a very easy way to like separate responsibilities so that apps can kind of like handle user privacy and user access better. And so yeah, there's more we can talk about with that whole like user access to these networks. But that's the gist of it for how to actually develop a Web3 API. And then if you'd like to build it, the command looks like this. You do Web3 build, and then you give it IPFS, a graph node, and then an ENS address. And this is for a test ENS address. But you could imagine that you could do that in production. Does that kind of make sense from the user perspective as the protocol developer and then also the dApp developer?
Yeah, so the runtimes are local. So this was
Yes.
I gotcha.
Mm-hmm.
That is genius.
Yeah. Mm-hmm. Yeah, and if we go back to this architecture diagram, it may make a bit more sense. Basically, here here's the application, and so this application is written in any language, and it has that language's implementation of the Web3 API client. So let's say, for instance, we're in Python. We include the Web3 API Python client, and then the Python client. The goal is to make these clients extremely simple to write. And so the Python client understands how to parse a query. So it has a query resolver that can figure out what you're trying to do, whether it be query a subgraph or execute a WASM module. And then if it is execute a WASM module, it will be able to fetch the Web3 API from IPFS and then it'll load the WASM module and execute it within the virtual machine. And WASM virtual machines exist in all these languages, and they're very lightweight. And so it's not as crazy of a thing to imagine running WASM in some other application as it is to, like, running the V8 JavaScript runtime, because the JavaScript virtual machine is very heavy duty and very hard to embed. With WASM, it's not that way. It's very lightweight, very easy to embed, and very fast. And so here we're actually executing all that logic of how to use the protocol, how to use these different peer-to-peer networks. And then we have these peer-to-peer integrations for, maybe this WASM module wants to interact with IPFS or Ethereum or a subgraph. Yeah.
Jordan, I have
Yeah.
a question. It might be a dumb one, but yeah.
No dumb questions.
If you want to, for example, write write the Python library, okay, for Web3 API, I would need to first of all find a library that converts Python into WebAssembly.
No.
No, how
So
does that works? Like,
yeah.
I want to write my library in Python, right? What do I need to find? Yeah, what I understand is that like with assembly script, okay, which is the one that the client has been written, converts basically, yeah, assembly script into WASM.
So
Yeah.
yeah. So I think that there's a big distinction that must be made between what the client is and what the Web3 API is.
Okay.
So see how up here in the Web3 API, we have mutation.wasm and query.wasm? These are the modules that are written in WebAssembly. And so this is where it's written in assembly script. And then down here in the client, this is written in whatever your application is written in. So let's say we're writing an application in Python, you would have a Web3 API client in Python. And what it does, and so now, like, how do these two things mix, right? Like, all right, sure, we have WebAssembly up here, which is doing like a bunch of protocol logic, sending transactions and things like that. And then we have a Python client down here that's parsing queries for the app. And then how does it bridge? What it does is it then passes the query's request into WebAssembly. So it's like, all right, we're calling set data. Let's call set data on the WebAssembly module. And so it's calling into the WebAssembly virtual machine that is running this module. So this module is running right here in the WebAssembly virtual machine. And then the Python code is calling into it. And this WebAssembly virtual machine is written in Python. So it's a you could think of it as a language interpreter, where it's interpreting and executing the code at runtime. So yeah, like the WebAssembly virtual machines are already written for us. There's lots out there that already exist. We would just choose the best one for Python, and then we would load our module into it and then execute against it.
And in Python, I would need to define like the adapters to communicate with the custom methods you create in the WASM. Like, for example,
Yeah.
Right. Does that make sense?
Yes, that makes perfect sense. So yes, that's absolutely the case. And then there's more to talk about on that topic, because if we think about having all the peer-to-peer integrations implemented in Python, that then makes this client very big, right? Like, it bloats the client.
Okay.
Because now all of a sudden this Web3 API client includes like a full IPFS library, a full Ethereum library, a full Cosmos library, et cetera, et cetera. So the idea is to make these integrations is to write as much of them in WebAssembly as possible. So that way, in the client, it can only have like simple kind of stitching logic. to be able to provide the Ethereum integration module access to a private key to sign, let's say. But that's kind of it that's inside the client. So the goal is to keep the client as lightweight as possible and write as much in WebAssembly as possible so that way it can be used in all the clients. Because we want these clients to be super simple to author and maintain. And like even after we add new networks. Like the ideal situation is if we added Bitcoin or Cosmos or Polkadot tomorrow, we wouldn't have to modify all these clients. They could all just stay the same.
Okay. Okay. Thank you.
Mm-hmm. Cool. So that's that. And if there's no more questions about like the app developer experience and the architecture, I could jump into a little bit of what the code looks like in the packages. But yeah, feel free to speak now or forever hold your peace. All right, cool. So, and Nick, was this scheduled for 30 minutes or an hour?
An hour.
Okay, all right. I don't know if I'll have that much content, so I'll just walk through this really quickly, and then yeah, we can probably stop a little early.
Sounds good.
So in the repo, this is the structure of it. We have our packages. We have a CLI, which just quickly to look at it, we have our commands where we have build, query, and the test environment. And then we also have, just some like staging level commands where we're still working on the implementation of these, but we'd like to be able to support like authenticating with different services, like let's say, Etherscan, or putting in a private key to be used on mainnet, or some other services you want to auth with, and this would just basically store those credentials in your local key store. And so we would use like secure private key storage locally to be able to access that stuff. And then for create, the idea here is to be able to like scaffold a new project. So the same way you can do like create React app, we'd like to be able to do like create Web3 API, and it'll scaffold out the protocol directory, and then maybe also like a web app or something like that. And then publish is to be able to, I think that this one is deprecated because I think that we're moving it all into the build, but this would just be to do like the publishing step of the build command where like it publishes it to IPFS and other things like ENS. So that's the CLI. For the JavaScript client, it's pretty straightforward. Basically, we have the core class, which is Web3 API, and this basically just exposes some getters and setters, and then it has a query function, and so this is kind of like the primary query function to be used to execute a query against Web3 API. These portals are pretty lightweight. For the subgraph, all it's doing is you construct it with a provider string, and then it executes a query against it, just a HTTP GraphQL query. For IPFS, it's pretty straightforward. You initialize it with a provider, and then you can do all the different IPFS commands. It just uses this IPFS library that's made for us under the hood. And then for Ethereum, the same thing is that you initialize it with provider, and then you can also give it like an optional signer or an optional ENS address. And then you can then call things like get a contract with an address and an API, or you can deploy a contract, call a view, send transaction, et cetera, et cetera. So this kind of wraps Ethers.js for you. It uses Ethers. And so here's the portals that the user initializes and passes into the Web3 API. And then the last step of all this is that you need to be able to stitch together the that host interface. So the host interface looks like this. Sorry, one sec. Host interface for Ethereum, let's say, looks like this. This is assembly script code here. And so this compiles to WebAssembly. And these functions, this is like the standard interface for the Ethereum integration. So we have call, view, send transaction, and deploy transaction. And so when the WebAssembly code calls this function, we need it to break out of WebAssembly into into the host environment and actually, call into the portal that will deploy this contract. So let's look at what that actually looks like. So here we have the WebAssembly Stub function. This is just a declaration. It has no implementation. And then the implementation is inside of JavaScript. So here's the JavaScript code for the implementation of send transaction, or deploy contract. And so in WebAssembly, when you call this function, it's actually going to end up calling this function right here in JavaScript. And then what it's doing here is it's reading from the WebAssembly memory. So this is like, it's basically marshaling the memory between the WebAssembly virtual machine and the JavaScript host environment. Because if we go back to this diagram here, inside of the WebAssembly virtual machine, it has its own memory space. So everything that's executing here is using its own heap. So it is not sharing memory with the application. It's a subset, like a secure subset. So whenever we want to access things in there, we have to actually read values from it. So here we're saying WebAssembly, read a string at this location, at this pointer location. And so, for this call, we pass in an ABI string. When it executes here, it gets turned into a pointer, which is just a number, a place in memory, and then we have to actually read it from memory and get the actual value. And then once we have our values read from the WebAssembly virtual machine, now we can actually execute it against our portal. So here is our JavaScript Ethereum portal, and we can say deploy contract with ABI and bytecode. We get the result, we write that result to the WebAssembly virtual machine, and then we return that result to the callback. And so, yeah, this brings about like a really, a really interesting and hard problem to solve robustly, which is marshaling memory in between the different memory spaces. And so, to quickly just drill in on this of why this is an issue. We couldn't just in assembly script, which again compiles to WASM, we couldn't just create our own like plain old data type where it has like a public value number and then public other string. We couldn't just create our plain old data type here and then be able to pass that in as a argument to this function. And the reason is because when we pass in a high-level data type that is not a base-level data type, like a number or a Boolean, and I think that's pretty much it. Like it's any type of number, any type of flag, or like an enum. It's going to turn this into a pointer, like because that's what it actually is. Like when you say new POD. It actually, allocates memory in WASM. And so this POD, even though you're saying, POD.value, like you normally would, what's happening in the compiled WebAssembly code is that it's saying, okay, so this pointer value is at like 0x8. So it's saying 0x8 plus the offset of this value. So plus the offset of this value. So let's say like 0x1. So this is like the starting of the value, and then it also has the ending of the value to read. So it's like, read, to, and then from, or from to. And it's going to actually read this from memory, and then we have like 0x, whatever the length of this value is. So like let's say like 32 or something. So basically what I'm getting at here is that pointers are a thing, right? Like just like they are in any other like native language. And so when you pass in this as an argument over here, we get a pointer to a plain old data type class. So when we actually load it from memory, it's no longer just a string. Like we're not reading a string. We need to actually replace this with a read plain old data type, and we need to understand how to read that from memory. So we need to understand the layout of this memory. So that whole problem that I had described to you, it's a problem called marshaling, like marshaling of memory from one memory space to another. And currently, the solution that's implemented for this is very straightforward. It only supports strings. And in the future, I'd like it to be more robust, to be able to support generic data types. And so that's something that is not currently implemented and will need to be implemented for this to be like a much better solution. And yeah, it doesn't just go for these interfaces. It also goes for your protocol as well. So inside of your mutation, if you wanted this, this value to, instead of just being a number, for it to be, again, like a plain old data type with lots of fields, you'd want to be able to do that. Like you'd want to be able to say inputs, POD, value, string, and then you'd want to be able to pass that as a value. We want to support this. And so in order to support this, we need to be able to marshal generic data types to and from the WASM virtual machine. So that's an interesting problem that was hit when developing this, and we're going to need to solve into the future. But yeah, so that's interesting, and that basically covers like the entirety of the client. Like what the client is doing is it's stitching together the host interface with the portals inside of the Web3 API. Do you guys have any questions on that? Cool.
So now DApps have DAPIs.
Yes, 100%.
Web3 APIs, and anyone who's creating a new project has an incentive to create this DAPI for the community to use.
Right. Yeah, and people are already doing this. Like there's lots of JavaScript wrappers for protocols to make it really easy for app developers to build apps on protocols. And so the shift that we're trying to make here is to make these JavaScript wrapper SDKs a Web3 API, so that way people can use them in any language, with a much lower learning curve. Because you no longer have to figure out, okay, like how does this JavaScript library work? How does this JavaScript library work? Oh, it requires these dependencies. This doesn't build right with my application. Yada yada yada. You instead just say, okay, what does the GraphQL schema look like? Cool, let's query that. And with the added benefit of it's accessible in any language, not just JavaScript.
Totally.
Yeah. And so that's the client. And then the last thing that I'll touch on is, well, so the client test environment is just like that's the test environment I ran in the background. It's not up right now, but it has like a dev server for just some helpers, Ganache, IPFS, and GraphNode. And then the last kind of meaty piece here is, and it's not too much, but it's basically just the interface and WebAssembly. So in WebAssembly, when we're using the protocol and we say, Ethereum.sendTransaction. What is this Ethereum class, and how does it actually boil down to that, underscore W3 underscore ETH underscore send transaction that we saw earlier? So this is the WASM runtime that just makes it easier to use Web3 API in your runtime. So if we look at what that looks like, in the index, we're exporting all these different types. If we look at, for instance, like Ethereum, there's a class Ethereum with all these static functions. And then send transaction boils down to just like the standard Web3 API call through the ETH interface. So it's just a nice helper library that's wrapped around these different protocols. And then,
Do you plan to, package, so those different providers, are those, is there a plan to make those different packages, that you can find on the Web3 Hub as well?
Yes, totally. So currently, like you point out, a really great thing is that all of these providers, all these different portals are bundled into the Web3 API. So if you're only using Ethereum, currently, you're going to download the Web3 API and get IPFS and subgraph libraries that you don't need. And so in order to make the Web3 API client very small, we're going to make these separate modules. The same way you would, let's say, in Webpack, you would include different Webpack add-ons.
Right.
You would do that same thing here with different peer-to-peer networks. And the same thing goes for not just the client, but also for the WebAssembly. We want to have these different host interfaces in separate packages. And we want to, let me bring back up the architecture. When we download the Web3 API into our app, we want to be able to query and basically say what plugins or what integrations do you require for your mutations? Oh, you require IPFS, Ethereum, and Cosmos? Okay, this client doesn't have a Cosmos provider, so we can't actually execute this Web3 API. So being able to query these modules and see what interfaces they require, and then seeing if you have compatible interfaces within your client. The other great part about doing this is that you can now have granular capabilities. So let's say that I wanted to instantiate my Web3 API client in C#, and I only wanted it to give it read access for Ethereum. And so I could do that at the time of creation. I could say create Web3 API with an Ethereum portal and only give it read access. And so now I can be sure that at runtime, if I try and query a Web3 API that requires write access to Ethereum, it'll error and it'll say, hey, I can't access these interfaces because I don't have the capability to.
And so would there be I'm sorry, I lost my train of thought. Execute GraphQL. Right, so would there be a Web3 API client that just wraps an Ethereum IFPS wrapper and in the graph and just lets you, it doesn't have any other functionality except for it to be that compilable library in that language, through those portals, just a generic Web3 API package.
Oh, right, that only uses Ethereum IPFS in the graph?
Right, and all the queries are written in the D app.
Right. Yeah, totally. So that's that. Whether we provide a client that does this, the idea is to not have to pre-bundle things for the user and kind of just expect what they want. Instead, what we want to do is we want to be able to have a single client, a base layer client that can handle all of these things without having these extra modules added. So without having to include Web3 API / the Ethereum client. And how do we do that? Well, we move all of the JavaScript code for Ethereum into WebAssembly. So that way you no longer need Ethers.js, you no longer need any JavaScript code relating to Ethereum. Instead, you would just provide the Web3 API client with a signing key, let's say, and then it knows how to download the IP or the Ethereum WASM module and then use that
Gotcha.
that integration. So yeah, like trying to not have to go the pre-bundling route of trying to say like, okay, here's like your Web3 API for these networks or your Web3 API for these networks. Like we want the base client to be able to do everything possible except the fringe cases, which people want to do custom development work to support. And that's how we achieve this vision. Like, if you think about it, like if we visit uniswap.eth and let's say that they're using Cosmos, but our Web3 Hub app doesn't have the Cosmos portal, what are we going to do? Like that's a case that we want to limit as much as possible. And so how do we do that? Like we build Cosmos into this I guess you could say a peer-to-peer network integration system where it's based off of WebAssembly, so that at runtime we visit Uniswap. Uniswap says, oh, I require Cosmos and a Cosmos signing key. So maybe as the user, you just have to provide a Cosmos signing key, but you don't have to do anything else. Like we don't have to rebundle the Web3 Hub application because we want to support Cosmos now. Like it can just download the Cosmos integration from IPFS. So yeah, it's kind of like how you download apps on your phone. You know, like we want to be able to do that same thing for different peer-to-peer networks, and also peer-to-peer protocols, and also smart contract protocols.
Gotcha. So would like Aragon create a Web3 API package?
Yeah, yeah, they would create a Web3 API. So yeah.
Okay, now I understand.
Yeah, so Aragon would be in place of the simple storage. They'd create their own protocol and they'd create their mutations and their queries. Cool. All right, so we're coming up on the end. So yeah, sorry for getting a bit in the weeds there. But yeah, there's a couple more interesting problems that I didn't touch on. If you wanted to just like look through the Web3 API prototype issues, if you go to the issues, if you sort them by like prize 0, so label like prize 0, these are all like the core issues that need to be solved that are blocking production. So you know, the heap manager, like the two-way marshaling of the types, like I talked about, is a big one. These other things are big as well. And yeah, so, but then, you know, after that, we can get into the fun stuff, which is like, you know, a script tag embed where you can just, you know, include a simple script tag and boom, you have a Web3 API in your HTML app. Fun stuff like that. So, but yeah, that's pretty much that. Yeah, if you have any more questions, feel free to ask. But if not, thank you all for listening. Thanks for coming.
Very cool stuff. Thanks for sharing, Jordan. It's awesome.
Yeah, of course.
Yeah, thank you, Jordan, for sharing, and thank you everybody for coming. I don't know who's giving the next tech talk. Next month, nobody's signed up yet. Nestor is a maybe. So yeah, let me know if you have a topic or anything you'd like to present on, and we'll get you on the schedule. Thanks for coming.